My dear students, this is 40th lecture and in fact last lecture as well in the series of mechanics of metal forming, and I am very happy to declare before you students that the last lecture that we are going to deliver today before you, as in continuation with the previous lectures, especially the lectures that was based on finite element method, a basic concept, and how this is going to be used as a modeling technique for metal forming processes. So, if you recall, two-dimensional cases we considered, almost most of the basic thing we discussed, and last lecture in 39 we also discussed the 3D cases. Now this lecture is especially devoted for 3D case for real life problem of extrusion that falls into the domain of metal forming, and this work is our own work in fact. So I am also glad to share with you the details of this. No doubt the whole work has been very long, but it has been cut down so that it can be put before you. So during the slides I may go faster sometimes, requesting you to please read the details on the internet itself and through your user interaction with the site, so that I can cover the whole things here before you. So with this aim, let us see the situation where a rigid plastic formulation is proposed for designing dies of extrusion die, especially for 3D case, and that too 3D case which is generalized in nature, and we would restrict ourselves to the cold extrusion case. So this finite element method analysis 3-dimensional case, which is generalized for any shape, for general especially non-reentry extruded product shapes, is going to be delivered. Please recall the upper bound modeling technique when we discussed. We also discussed the upper bound modeling for a generalized extrusion shapes. Any kind of extrusion you can model with upper bound we discussed. So based on that itself we proposed, if you remember, a slicing algorithm and then many other things if you recall. So what we did there, if you recall, the geometry, whatever geometry you want to draw or you want to extrude, you used to draw using line, arc, circle, polyline and ellipse entities of AutoCAD, right, and the corresponding DXF file is created. Once process this DXF file and necessary data are then separated for feature recognition, and the extrusion analysis. If you recall this, we covered. So, the feature cross section is again broken into number of smaller elements to form number of 3D slices. I am not going in details of those technique now. You can go back to those lectures. The sliced elements are taken one by one for the proposed rigid plastic finite element analysis using 3-dimensional finite element method. This finite element method particularly will give the strain rates, velocities and pressure as different nodes to estimate the extrusion power and average pressure for optimal die design. As you know, die design is very crucial and an area which is full of art. Still the whole thing has not yet been explored. So, this process will extensively help in die designing, and whatever result we obtain with this analysis, it has already been tested with experiment, and it is found that it is good enough and one can rely on this. So, we would then start with the non-reentry shape, and as you know, once you are able to do it for non-reentry, you can apply for any reentry shape as well, and also you can club the heat transfer part with this. It is easily the process can also be extruded for hot extrusion case. So, with this aim we will do, and please remember the feature recognition concept again to remind you. The process of optimal die design work, and you know we get the strain rate, velocities and pressure, all that, and the earlier experiment, some of the experiment by Young and some of the Kiuchi and all those things, as well as the theoretical work, and also a software which is called as the Hyper Extrude, which is inbuilt domain or inbuilt module of Altair engineering group. So, that one can also refer. So, now look at this figure, the block diagram. Just to remind you that this block diagram shows the process, how do you go ahead with recognizing features in a given shape, because you may solve it for a single hole extrusion or multi-hole extrusion. So, this figure, the block diagram shows the details of the processes that you may go in detail later. This figure number 2 shows the construction of a power element for a general non-reentry shape. This figure has come earlier also, but to refresh you and remind you before starting, I am giving it to you here. So, you can see the billet side and this is the product side. We are considering the only die portion, we are not considering any other tooling. So, this finite element method, it is limited to that. One can extend it for others as well. So, this is what is the one of the slice of generalized shape and rigid plastic FEM formulation. So, if you look at the A gives the typical brick element, which is 20 noded brick element, and there the two types of nodes are there. One as the darkened nodes that represent the pressure nodes, and the velocity nodes that represents, which is undarkened, so that represents the velocity nodes. So, you can see one of the slice and how the elements are going to be constructed, right. So, the B part shows the boundary, one of the boundary element on the of these, right. So, you can see here one thing, the A, B, C, D, all those marking, and so you can see that Ij along the axis, if you see the length of the Ij, that is the initial billet length rather, and the Kj is the length of the product length outside, and Jk is the actual die length, right. So initially it is proposed that when we start with the meshing, we take care that Ig is equal to 3 times of the Jk and Kl, and that is further equal to 3 times of the Ke. This is a basic assumption which is there. So as you remember, how do we start? So to start with, one had to start with the constitutive equations, right. So the constitutive equations of plasticity, especially for large deformation plasticity, where the elastic the strains are neglected. So one can, this is what's the equation number 1, the constitutive equation, where the strain rate, that is the epsilon ij dot, is defined for ij to be x, y, z, r 1, 2, 3 it can be. So vi and vj are the velocity component along ij directions in Cartesian coordinate system. So the constitutive law which relates Derivative stress tensor, that is sigma ij prime, and strain rate tensor, that is epsilon ij dot, and the Levy-Mises coefficient nu for rigid plastic material yielding according to the one Mises yield criteria is given by equation number 2. So you can see, I am not going to now read these equations, you can see on the screen of the site. So the generalized stress and the generalized strain we discussed earlier also, it is given by equation number 3, and then one can find out the generalized strain from equation number 4 here. So look at this figure number 4 here, where the division of the one slice into finite element for the analysis is shown. Now you see how the slicing, one slice, and in the die region how the division and elements and nodes are. This shows one of the such division of the nodes and elements. So then one can proceed with the weak formulation, right. So in this case we are going to choose the mixed pressure velocity formulation, and in the where Vx, Vy and Vz and P is the function of that satisfy a weak solution if the following integral is satisfied, that is this integral which is shown here in equation number 5. This is what is being in equation number 5. So it is a summation of long equation, you can see, where Wp, Wx, Wy and Wz are the approximate weight function. Since hydrostatic pressure is compressive and hence negative, and the weighting function Wp is also taken negative. So performing the integral by part, we get equation number 6 here that has been. So that is the integral over the volume I1 plus I2 dx dy dz minus integral over the volume I3 d A1 minus integral over the volume I4 dA2 minus integral over the volume I5 dA3 is equal to 0, where I1 is defined this way and then I2 is defined this way, I3, I4 and I5 is defined in equation number 7 here, right. So, and dA1, dA2, dA3 is also defined in equation number 8 here. So, and other terms like epsilon xx rate is defined, like epsilon yy rate, that is the strain rate, and corresponding weight function is also defined in equation number 8 here, 9, equation number 9, you can look all these things. So, if you integrate and then in the finite element formulation, it is convenient to express the integral in the matrix form. So, this matrix is shown here in equation number 10, right. You see the whole equation which was presented in equation number 7, that is now converted into the integral form, right, in equation number 10 here, where m is a vector having 1 1 1 0 0 0, then strain rate is another vector which consists of these components, and strain rate weight function is consist of these one. So, starting with the finite element approximation, a brick element is used here, okay, with 20 nodes in each corner. However, since the essential boundary condition is to be satisfying, the continuity equation has to be satisfied. So, primary variable velocity is taken as at each node to be continuous inside the element, but the pressure variable is taken constant within the element, right. Another possibility is taking safe function for velocity as the quadratic, and the pressure for the pressure it is taken as linear at each corner nodes, right. So, for nodal velocity 20 noded, and for pressure 8 noded elements are selected, alright. So, as far as the shape function is concerned, the square shape function has 20 noded element, which is shown here in this figure with the corresponding master element is taken for velocity, and 8 noded, which is shown again here in this figure, for pressure is assumed constant over an element. So, this figure shows the surface element, that is 8 noded for the velocity and 4 noded for pressure, if you look at the boundary one surface along the dibillet interface, along with its corresponding master element, right. So, here please recall back whatever we covered in the previous lectures. I am not now going in very details. I hope that you now understand. So, the natural coordinate for the 20 noded and 8 noded element are to be there, and this is what is being shown here. So, for 20 noded the natural coordinates are given here, okay. So, like node 1 it is minus 1 minus 1 minus 1, node 2 it is minus 1 minus 1 1, 3 it is 1 minus 1 1, and likewise 10 it is 0 minus 1 0, and likewise 20 the natural coordinate system is 0 1 minus 1, okay. So, you can also look at this figure. So, the functions, the shape function is given here, Ni as 1 by 8, and in terms of the natural coordinate system it is given Ni and Nj. So, I varies from 1 to 8, and j varies from 9, 11, 19, 17, right. So, this equation is shown here as 11, this safe function, and the previously it was given for 20 noded the your natural coordinates and the corresponding mapping. This shows the 8 noded natural coordinate and corresponding mapping. So, 8 nodes in natural coordinate is shown here, and the corresponding safe function Ni is also shown. You can see here I is from 1 to 8. So, the safe function for di-billet interface are to be also there different, and this is chosen as 8 noded as given in this equation number 12 here. Okay. So, Ni is given here and Nj is given here. So, Ni is for I 1 to 4 and the Nj where j is 5 and 7, and Nk, it is when k is 6 and 8, the safe functions are different, right. So, looking into this, then one can propose the Jacobian matrix. So, the Jacobian of the thing, the corresponding matrix is proposed in equation number 13 here. You can see that is deva x by deva x deva x by deva zeta, deva x by deva y by deva zeta, deva z by deva zeta, and all that, and that is simply written as j11, j12, j13, j21, j22, j33, 23, j31, j32, and j33, and where the deva f by deva x, deva f by deva y, deva f by deva z becomes J inverse matrix, and the corresponding deva f by deva zeta, deva f by deva eta, and deva f by deva xi. So, this is again given here. Determinant of this J is calculated by this equation number 14 here, and then the inverse of the Jacobian J matrix is determined, which is shown here in equation number 15 here, right. So, for boundary nodes where the di-billet interface exists, one can find out the value of A, and then determinant J is defined as under root A square plus B square plus C square, where A is A, B and C, which is used to determine the determinant J here, is shown here in equation number 16 here, right. So, then we start the finite element formulation, especially for strain rate and the strain rate weight function. So, this strain rate vector is given here, that is the 6th vector, that is a epsilon dot xx, epsilon dot yy, epsilon dot zz, and under root twice epsilon dot xx yz, that is the shear component, and this is what is shown here in equation number 17. Now, applying an arbitrary function f, which is a function of x, y and z, to, so that f x y z becomes f x in terms of the mapping if you take. So, the f x zeta eta xi, then y zeta eta xi, and z zeta eta xi. So, that is the arbitrary function f that maps the two coordinate system x y z and natural coordinate system. And then if you differentiate it, so and once you define the y, z and x in terms of the safe function, So that is what has been shown here in equation number 19. Okay. And then the Vy, Vz is also specified, because the velocity has to also be defined in terms of the shape function, and that is defined in equation number 18 and 19 here, and 20 as well, 18 and 19 here. So taking an arbitrary function f, as I told, which is a function of x and y z, so one can now differentiate in this fashion, which is shown here in equation number 21. Now you look at J is your Jacobian matrix. So the whole thing becomes the vector of, that means dy f by dy x, dy f by dy y, dy f by dy z is equal to J inverse and dy f by dy zeta, dy f by dy eta, and dy f by dy psi. So that becomes your equation number 22 here, right, where J inverse and Vx, Vy and Vz, if you look at, then one can then say that the equation is for the strain rate vector becomes as shown here in equation number 23. So now you see how many component has appeared, where because Vx, Vy and Vz is written as shown in equation number 24 in terms of the corresponding mapping along with the shape functions. So one can find out dy Vx by dy xi, that is the derivative with respect to the natural coordinate system. So this is shown here in equation number 25, and then the whole strain rate is converted finally in this form, which is shown here in equation number 26 and equation number 27. Alright. So the strain rate vector now it is available in as shown in equation 27. So now here if you see this vector, it has b11 0 0, b14 0 0 and all those things long. So the size is around 6 by 60. The elements of this matrix is 6 by 60, where b11, b12, b22, b33, b41, b42, b452, b561, b other components are defined here, right. So this is what is shown in equation number 28. Alright. So you can look into these details. Then one can then simply write that the strain rate vector is the matrix B multiplied by the vector V, the velocity vector, and this is what is shown here in equation number 29. Similarly, the strain rate weight function vector can also be defined, and this is shown in equation 30. Therefore, the Vx, Vy, Vz vector can be written here, and that is simply Ni vector matrix multiplied by V vector, and that is what is shown here in equation number 31, where the weight function vector corresponds to your Wx, Wy, Wz components, and that is nothing but the Nij, Wij. So that is in equation number 33, and the pressure corresponding to the pressure nodes is defined as the shape function Ni matrix multiplied by the pressure vector corresponding to the each element, and this is what is shown here in equation number 33. Okay. So, the corresponding weight function for the pressure node is again shown here as equation number 34. So, secondary element are approximated by taking an 8 noded quadrilateral element, as I said, and this is what is shown here. The tractions as Tx, Ty, Tz again in terms of the shape function. This is shown in equation number 35, and by substituting all these matrices along with approximation for the boundary element, the final finite element equation is written here in equation number 36. So, now you see a large component of the integrals. So, you can see on detail, I can't read here now, and hence the other slightly manipulated form is written in equation number 37 here. The whole finite element equation, assuming that the K matrix K11 is 0, matrix K12 is shown as the integral of this one. Similarly, the matrix K11, K22 and all those things are shown here, and the weight function vectors is also shown here. Now you can look at, right. So, the weight function W, the vector, then the X vector, then the F vector, especially Fx, Fy and Fz vector, and then the element stiffness matrix vector that consists of vectors that consist of matrix K11, K12, K21 and K22, right, where the X vector is consists of the pressure, nodal pressures and nodal velocities, right, and which is defined there, that the P1, P2 and all those things. Then Vx1, Vy1, Vy1, Vz1 and similarly Vx2, Vy2 and Vz2 and all those things component. So, that is written the corresponding to the vector x, right, and therefore, finally these are written in equation number 39. So, this is what is the final finite element equation. So, now you see the integral has been converted into summation, right, and that consists of all matrices. Okay. This is shown here. You can see the details is staying and giving more time to study all the terms shown here in equation number 39, and then subsequently the same thing in other form is written in equation number 40. Here the integration is transformed to summation by Gauss quadrature integration technique with 3 points, right. So, 3-point Gauss quadrature technique is used, and then one can see where the again determinant J, that is J is defined as in equation number 41, and the other components that is the determinant J, again same thing previously I discussed, same thing is written here in equation number 42, where and the ABC terms and then all those things. So, it is almost repeated again, and then the traction along the die billet interface are here, that is the mod of the shear the stress is function of your mod of the normal stress, and then equation number 45 gives the f vector, that is the fx, fy and fz, and that is what is being shown here. So hence the final equation becomes what? This final equation becomes as shown in equation number 46 here. That is the summation where over the all nodes, then you have the weight function vector, then the k vector, that is the stiffness matrix vectors, multiplied by the x vector, and that becomes the summation over the over all nodes, which is again the weight function transpose multiplied by capital F vector. Or the same way is written in another form in equation number 47 here. And then finally the same thing is shown here in equation number 49. So now the final format, it looks like same as we started with previous equation. So here the x vector, that is the unknown, becomes equal to the stiffness matrix inverse multiplied by the force vector including all the terms. So that is what has been shown here in equation number 49, right. Then once we have established the finite element equation in matrix form, then one can go ahead with the boundary condition. To show you the boundary condition of this one slice, refer this figure again. So the various boundary conditions which is shown here is defined like the first one, the entry and exit boundary conditions, that is on the entry phase A, E, J, right. So here we have Vx is equal to Vy and that is equal to 0, and Vz is equal to Vz, that is, and on the exit phase, that is DHM, the Vz is equal to Vy is again 0, and Tz is equal to Ty, and that is again 0. Second boundary condition is on the di-billet interface BCLK. If you look at the figure, where the Vn is 0, that is the normal velocity is 0, and then Vn is, in fact, it is defined as your Vx, and the n and the unit vector, and the summation means V1, V2 and V3 multiplied by corresponding normal, unit normal, and that has to be 0. So that is shown in equation number 52 here, 53 here, and where the constant friction case, in case of that, when the friction is taken as constant over the die interface, so in that case the mod of the yield stress is must be equal to taken as m multiplied by generalized stress divided by root 3, right. So this what we have already considered earlier. So the third boundary condition comes to the billet container interface, that is ABKJ, where the normal velocity is 0 and Tx, Ty and Tz is also 0. The fourth boundary condition occurs at the free surface, that is CDML, alright, where the V normal is 0 and Tx, Ty, Tz is also 0. Fifth velocity boundary condition comes along the neutral axis, that is EFGH, this neutral axis, where the center of or the center of gravity of the geometry falls. So there Vx, Vy, Vz is 0 certainly, because the V normal is 0, and also Tx, Ty, Tz is also 0, okay, and the last one, which is the contact surface, that is EHDA and EHMJ. There also the normal velocity is 0. Okay. So, keeping these 6 boundary conditions, one can now propose the solution methodology. So, we have already done it. You may also try with these formulation. So, these boundary conditions are imposed on the final equation at specified nodes. So, you recall there are 20 nodes for velocity boundary conditions, velocity nodes, and 8 nodes for pressure, okay, and then there are other nodes corresponding to the surface element, right. Then the resulting equation is solved iteratively by household method. There is a household method for solving equation as well. So, initially for first iteration, a suitable guess value for nu, that is the Levy-Mises coefficient, is given. Then the result which is obtained after the first iteration is used again for further iterations. Then the iteration is conditioned until the nodal values of the pressure and velocity converges between 0.1% between the successive iterations. So, we go ahead till that. The flow formulation results data is in fact used to in cold and hot extrusion analysis. The safe extrusion product that comes out may have many power element, as I told, and we have started with the same. So, only one power element is analyzed here at a time. Otherwise, it is very difficult to solve the iteration with the available compiler or computer at a time. So, it is chosen to take one element, and using this procedure one can go. The segmentation procedure and the formation of number of power element concept, it is again chosen from the same work previously that we did it in 2002. So, and then based on this procedure, a program we have already developed in Fortran, and we solved for an axis symmetric rod consisting of 24 power element, and we have tested the applicability of this proposed FEM methodology, and then it was also validated with Young et al. 1990 work. The listing of the program and all input and outputs, one can, if anybody is interested, you can contact me, we can share. And I would like to show you some of the result that we have got using this program. So, for an example, if I take this example where Young and the co-worker in 1990 conducted experiment for axis symmetric extrusion of circular sections. Details of the material specification and other process parameters are taken same as they have mentioned in their paper, like the aluminum alloy 2024 annealed was taken, and the stress strain relationship was taken as this one for aluminum, and the billet radius is taken as 12.5 mm, the friction condition is taken as 0.12, and the die profile was taken as the 4th order die profile, right, and then L by R 0 ratio, that is the initial die length, is taken as 2.0, speed of the RAM is taken as 1 mm per second and temperature is taken as the room temperature that is 20 degrees centigrade. So, all the final component geometry, in fact it is circular with the product radius as 12.5. So, different those results we conducted using this formulation, we got result, and also we took the result with hyper mesh also and we compared. So, whatever result we obtained at different reduction, this is shown here in table 1, and it is again in this table 1 we will show you where to compare the experimental results obtained by 1990 by Young and his co-worker, right. So, you can see here this is what's the comparison in table 1. So, reductions as 40, 50, 60 and 70, and the Young's result is shown here, and the result which we got by this one also we have got. So, no doubt our results are higher because we use okay. So, that means whatever the 3D formulation we have used here, the beauty is that any general extrudable solid shape can be used, and now it is analyzed including non-reentry and reentry, right, and this method can be converted into a good software as well. So, alright. So, the various power elements are taken one by one as I told for the FEM analysis, and this FEM analysis certainly will give the velocity and pressure field within the deformation region at various nodes. These velocity and pressure field are again taken as input for the getting the temperature and distribution if it is required, right. If suppose you can also use this pressure and velocity field and strain rate field with temperature, so you can go into the area of the hot extrusion as well. As we have done lot of results we got, and one can contact me if you are interested in more details of this. Okay. So, this figure shows the variation with the die length and the average extrusion pressure that we get, right. So, at various reduction, say here this reduction is shown here. So, you can see at around die length 1.5 we get the minimum extrusion pressure. Okay. So, this is what's the details of the 3-dimensional extrusion, and it is purely metal forming, which was the purpose for the course. This is a again to remind that this is a finite element method, a modeling technique. So, for you to go ahead into more details if interested, these two references can be used. So, this is the first reference which we worked, published in 2002 in ASME transaction, manufacturing science and engineering, and the second one is the Young's work 1990, which I mentioned here, and that was published in International Journal of Mechanical Sciences way back in 1990. So, you can get more and more details of this there. Okay. So, with this I am very happy to declare that this course is now closed, because we have covered the whole course content before you, and I appreciate you all that you heard me very carefully, very patiently. There are certain closing remarks I would like to pass on to you users, including students, using other users all over world. So the first thing is that I need your support in the form of feedback. So a feedback link has been provided on the web. You please give your feedback so that we are able to improve it. The second is that I would like to thank National Mission on Education through Information and Communication Technology, who supported this project for creating the e-content for all of you, which is supported by MHRD, Ministry of MHRD, New Delhi. And third one I would like to mention here, when we teach this lecture in large gathering, here also there are students, you people, but when we take this course before undergraduate, postgraduate, a group of say around 80 to 100 students, and where we say the real life lecturing. So this course, it depicts those frames as well here, but please remember that the real life lecturing is different. The internet, it will never substitute the real life lecturing in class, and that too on the board when we write, because there the emotion flows. In this kind of lecture e-course, there are few emotions, no doubt, and that you have to add from your side, only then you will recognize. But these emotions, when the real life lecturing comes, so one has to be very careful, and one has to be caution that while you study these lectures on net, you should be very much devoted. You should look only the delivery side. You don't go much the kind of people who is going to deliver, his tone, his language. So you should not be much careful. You should be careful about the content what is being delivered, and that is how the e-content, electronic content matters. So and then apart from that, your job is more than what you hear. So in basic, if you take 1 hour lecture on web here, fully devoted manner, then you need to further study 4 hours to be keep yourself perfect in that, right? And huge practice is also required in terms of the problem solving, in terms of the doubts clearing and all those things. So that's what's the difference between real life lecturing and then internet web based lecturing that is there. So this, and then the fourth thing I would like to remind, that there are certain advantages as well of e-course. The advantages like when we study through e-course, basically the India government and all over in world, the practice is that you don't have to pay anything, and only your devotion, if it is there, you can learn a lot. So that's a very good thing. On the other hand, disadvantage could be when you are purely dependent on the e-content, whatever is being delivered. You think that this is the only whole thing and I have gone through everything. It is not so. As I told, it is the only whole content. See, the whole course we covered in 40 lectures, alright. We could have covered this lecture, this whole thing in much more detail in 60 lectures or more than that. So this is what's the limitation. So the limitation of the course is that we had to finish within 40 lectures. So, keeping these advantages, disadvantages and limitations, you can further grow in this course, and with all my best wishes to you people for extending your knowledge further for the future for your benefit. And please don't forget to give me feedback. Okay, thank you.